Okay, so we've been looking at sampling models when the population was normal, or even for the binomial distribution where the population could be normal given certain conditions. So I should say approximately normal. What about when it's not normal? So first of all, I'm going to go ahead and look at a uniform distribution. That definitely is not normal. That's kind of uniform. I'll say approximately uniform. So I'm taking samples of size 5, right? And I expect a lot more spread for this because it's kind of uniform across the range, all right? And you can see, yeah, I'm still getting points. They do seem to be kind of close to the population mean. That's where the mean is, right? And, but you don't see a lot of points on the extremes over here or over here. Why is that? Well, it'd be very unusual to get all your samples from this side. Now, as I increase the sample number of samples taken, you saw it got normal. So there was the, oops, let me finish. So there was the distribution when the sample size was 5. Now I'm increasing it to 25. That actually looks pretty normal. So looking at that, now the problem is when you do 25, the animation takes way longer because you got to take the mean of 25 samples. There we go. We got 2 means. Now I get tired of it. I'm like, okay, let's do a bunch of samples. 10,000, 100,000. And what are we noticing? Well, you can see that the distribution for the means still looks approximately normal, even though my parent population was uniformly distributed. And the variance still decreases with increasing sample size. All right, okay, that was the normal. I'm going to do something crazy. Let's do a bimodal distribution, which really looks messed up. So you can see this one right here, right? Okay, so looking at that, here I'm just doing sample sizes of 2. And it's not so unusual with this distribution to get some extremes, is it? But look, I'm still getting some in the middle here, even though there's hardly any points in the middle. Why is that? Well, sometimes I'm getting one from each side. It's kind of like flipping a coin, getting heads or tails, right? And so for this distribution, let me continue playing here. For this distribution, you can see it's kind of like getting heads, getting tails, or getting heads and tails. So it's sort of bimodal there. When I went to n equals 5, it started to kind of get this combination. So this is like 5 heads. This is 5 tails. This is 2 heads and 3 tails, 3 heads and 2 tails, right? And then now I go to 25, which always takes longer to get my sample mean, right? And I get 1 point. So what happens is I take more samples and I say, okay, let me start getting some samples even though this animation's going. And what's going on? When the mean is 10, this is what I got. And when it's 25, look what happened. So 10 wasn't good enough. 25 worked pretty well for this crazy distribution. So this leads us to the central limit theorem. Basically, it says the sampling distribution model of the sample mean is approximately normal regardless of the distribution of the population, all right, as long as the following are met. So these assumptions and conditions. Randomization needs to be in a simple random sample to minimum. The sampling method is not biased. So same as before. 10% condition, same as before. Here's the new one, large enough sample condition. Recommend n is greater than 30 or 40, and that depends on your textbook source. Barron said 30. They said, well, it could be 40. Your textbook refuses to give you a number. And we saw it was roughly normal when we did 25. So don't take these as hardcore numbers, but you got to be getting close to 50. 10 is definitely not big enough. All right, so let's look at an example, some speeders, and we're still going to use the same statistics because we said it was approximately normal. Speeds of cars on a highway have means of 52 miles per hour and standard deviations 6 miles per hour and are likely to be skewed to the right because there are a few very fast drivers out there. Describe what we might see in the means of random samples of 50 cars. So here they want us to show them the distribution. We should be prepared to draw a model. From the question, we know the mean is 52 for the population, and the standard deviation for the population is 6. We are doing samples of size 50. So 50 cars, our assumptions are that this is a simple random sample or at least without bias. Now, if I did all these samples, say, Sunday morning, when the older people are out going to church, those speeds might be a little lower. But if I do my thing so there's no bias, we should be okay. And we're also assuming car speeds are independent. Kind of wonder about that one, because I have the feeling, when people drive faster, you tend to go with the pack. And when people slow down, usually like, oh, there must be a cop ahead, so you tend to slow down. Just saying. 10% condition. 50 is definitely less than 10% of the population of cars. The large counts condition. 50 is definitely large enough. All right, so let's do some math. Here's our formulas. The mean is easy, it's the same. Let's find our new standard deviation. It's going to be smaller than our population because we're going to divide by the square root of 50. We get 0.85. So that means my model for the means is a mean of 52, pretend that's, 52, and a standard deviation of 0.85. So I draw my bell curve, my normal distribution with my 3 sigma on it. And the way I would describe this is according to the normal model, we expect 68% of the samples of 50 cars to have mean speeds. Notice how they said mean speeds. If you said speeds, that's a different thing because you're talking about each individual data point. Here we're saying mean speed. So this is the means for our sample. Between 51.2 and 52.9 miles per hour, 95% of the samples have means between 50.3 and 53.7, and 99.7% of samples have means between 49.5 and 54.6. One more example, we're going to look at mean birth weights. So this is how you might use it. This is the really interesting application. So at birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds. A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? Now, if you were to ask me, what's the probability that the baby weighs 7.2 pounds, a baby, and you have a standard deviation of 2.1, you're like, oh yeah, sure, no big deal. But what is the probability that the average of 34 babies born there is 7.2? So let's take a look. First of all, here are our numbers. Our mean for the population is 7.8, standard deviation is 2.1, and we're doing sample size of 34. Our assumptions are 34 babies are a simple random sample, or at least without bias. That there's randomization occurring, that's another way to write that. Birth weights are independent. Should be. The weight of the next baby born doesn't really depend on the last baby that was born. Distribution is likely unimodal and symmetric. And that's one way you can say, hey, most times it's probably very close to a normal distribution, but this is something you can add in, not as required. 10% condition. 34 is definitely less than 10% of the population. And the large counts condition. We're going to say 34 is large enough. And probably, 34 is probably a little bit close. But since it's unimodal and symmetric, we should be fine. All right? And I remember I was able to use 25 with a bimodal. But that was that bimodal. So be careful there. All right. So let's calculate the standard deviation. We just divide by the square root of n, square root of 34, and we get 0.36. Look how much smaller that got. All right. So our model is a mean of 7.8 and a standard deviation of 0.36. So this is a model for the means. Okay. Now, Mrs. Overman likes her z-scores. So I'm going to basically do the average that I'm comparing, which is 7.2, to the mean of the population. 7.2 minus 7.8 over that new standard deviation, and I get negative 1.67. All right. So 4.7%, when we put this on a curve, is less than that number. So what we're going to say is, according to the normal model, only about 4.7% of samples of 34 babies are expected to have mean birth weights below 7.2 pounds. That's not 4.7% of individual birth weights. It's not unusual to weigh 6 pounds. It's not that unusual to weigh 6 pounds as a single baby. But for all the babies to average 7.2, that is unusual. The samples of babies near the factory appears to have an unusually low mean birth weight. Notice appears to have. We got a hedge. play politician here and make sure you don't say anything too definitive. So what can go wrong in this unit? First of all, don't confuse sampling distribution with the distribution of a sample, all right? So I've been looking at the books, and your book gave me some very specific advice. We should say sampling models. I like that. But really on the AP test, I don't think they're going to really say, oh, sampling distribution or distribution of a sample. They just want to make sure that when you're looking at means and statistics for samples and how those behave compared to an individual data point. So are you comparing statistics or individual data points? So keep that in mind. Beware of observations that are not independent. We should always be careful with that. Remember, with the speeders, sometimes you could say, hey, when you got a pack running fast, some of us tend to join in. All right. Watch out for small samples and skewed populations. If the population is normal, then a small n is like 10 is okay, right? We saw that actually in the coin flipping. But otherwise, use n greater than or equal to 30 or 40 as a rule of thumb. And again, you just say, well, it looks large enough. Make sure